Hello, this is Vedant Rai, SAP ID 60001180061 from B4 batch of TE Electronics. Today I will be presenting experiment number 4 of my DLIC practicals. The aim of this practical is to design a differentiator using OpAmp OP07, and we will also study its frequency response. We already know what a differentiator is. It is a circuit which produces output proportional to rate of change of input voltage. This is the general circuit of a differentiator using OpAmp. We'll now see how to design the circuit. We are using LT-Spice software. I'll first place my OpAmp OP07. Then I need my resistors. One resistor up and one here. Then I need my capacitors, control R, one capacitor over here and one over here. Now I'll connect the circuit. I need my voltage source. I also need two voltage sources for my VCC and VEE. Connect the resistor and the capacitor. And finally the positive terminal. And now I'll label the VCCVE. I'll right click here, label net VCC, put the VCC here, one will come over here, this one is actually the VE. I'll rename it, and this is also a VE. I'll now ground the open terminal, open ends of the circuit, ground. And I also need to label V out. And I place it here. Now the only thing left to do is assign the values. We have already performed the calculations to get the values. We have FA as 1 kilohertz and FP as 10 kilohertz in the problem. It's given in the problem. We assume C1 to be 0.1 microfarad. We can assume it to be any suitable value. FA is 1 upon 2 pi RF C1. Using that formula, we can derive the value of RF, and FB is equal to 1 upon 2 pi R1 C1, and from that we can get the value of R1 equal to 160 ohms. The formula CF is equal to R1 C1 upon RF. Using that formula, we'll get a proportional value for CF, which is 0.01 microfarads. R1 C1 can be assumed to be equal to the product of RF CF, and ROM is 150 ohms, but however we do not need the offset minimizing resistor in this case, because because in LT Spice we have an ideal OP07. Now I'll enter the values. Sorry, this capacitor will be 10 nanofarads. This one will be 0.1 microfarads, which we've assumed. This we found to be 160, and the VCC as usual will be 15 volt. We are performing the frequency response, so we will be giving AC supply. So we put AC amplitude as 1. We are now ready to run the program. So we go to simulate and do run. We have to perform frequency response. So AC analysis, the type of sweep is same as last experiment, decade sweep. The points we'll use as 1000. Start frequency we can use as 1 hertz. The stop frequency we can use as 1 megahertz. Okay. I click on the output. Yes, this is the we can hide this phase and yeah, this is the frequency response of the differentiator. As you can see, it's first constantly increasing until it reaches a value of around 14 decibels, 14.1 according to my one. At 10 kilohertz is the point where it reaches the peak around, and 1 kilohertz is the around approximately the point where it reaches 0 decibels. So this is the frequency response, and to see the plot, to see the phase, we right click here and then we hide the frequency response. This is the phase response of the differentiator. We'll now see what happens when we give a sine wave input. I've taken the sine as 0, 1 volt, 1 kilohertz, and I'm ready to run it. I click on the input and the output, and I can see the input is a sine wave and the output is a cos wave. The so it's the differentiator is working properly. Then I'll see if the input I've given as a square wave. These are the values I have used, and if I run it, we can see that input output, we can see that the square wave is producing not random, but is producing peaks. And finally, if I see the and finally we'll see the differentiator with the triangular wave input. These are the values I have used, and if I go to simulate and run and click on the input and the output, and we can see that the input triangular wave has given an output of a square wave. That's exactly what we were hoping for. These are all the graphs, and that's all for this particular experiment. Thank you for watching.